Good morning. This is Dr. Jingbo Louise Liu from Texas A&M University, Kingsville. Again, today we are going to working on the chapter 7, chiral molecules and the related chirality. Chapter 7, chirality. So in this chapter, we are going to essentially show you how to determine molecular chirality and how you are going to determine enantiomers, diastereomers, related chemical reactions, also about different projections such as Fischer projections. Particularly, we are going to focus on the absolute configuration of your chiral molecule with maybe only one chiral carbon. So first of all, we are going to discuss the molecular chirality related to the enantiomers. A molecule is chiral if its two mirror image forms are non-superimposable in the 3D dimensions. The word chiral is derived from the Greek word which means hand. Chirality mostly occurs in the molecule which contains a carbon. Those carbons are connected to 4 different groups. For example, if we have bromo, chloro, fluoro, methane, the carbon attached to a hydrogen, to a fluoro, chloro, and to a bromo. All of these 4 different substituents, they have different sizes, they are different elements. Therefore, you are going to find 2 isomers. They are called enantiomers, such as A and B. They are the mirror images, such as your 2 hands. Therefore, this molecule is called a chiral molecule. Your carbon is the chiral center. These A and B molecules, they are called enantiomers. The enantiomers meaning they are the stereo isomers. They have the same connections, but different 3-dimensional arrangements. Those isomers are related to an object and is non-superimposable mirror image. Again, 2 non-superimposable mirror images are classified as enantiomers. So in your enantiomers, you are going to do this. You will rotate the molecules in the space to check whether the representations are superimposable or not. If the representations are superposable, first rotate the molecules around so that your hydrogen in the same direction. You always put your hydrogen in the same direction and then you are going to rotate it. If the 2 molecules like this A and B, so you are going to rotate it, rotate 180 degrees, you receive your B. If those 2 molecules, they are not superimposable, they are non-superimposable, you call them mirror image. If you have your A, your original molecule, you compare with your B prime, your B molecule and A molecule, we believe they are mirror images, and you are going to rotate your B molecule by 180 degrees, make your hydrogen direction is the same as the hydrogen direction of your molecule A. So this B prime and A, what did you see? They are not the same molecule. Your bromo, your chloro, they are in the same position. Your chloro and bromo in the same position in 2 different molecules. In this case, you consider after rotation of your B. So the B prime and A, they are non-superimposable mirror images. Therefore, your original A and your original B molecules, they are enantiomers. So that's how you determine your enantiomers. In your molecules, you have your carbon, which are connected to 4 different other substituents, such as I consider carbon connected to W, X, Y, and Z. All of these carbons, though these substituents, they are different from each other. So therefore, this carbon is called a chiral center. This molecule is a chiral molecule. For example, if I have an alcohol, I have my 2-butyl alcohol. This carbon connected to a hydrogen, hydroxyl, methyl, and iso. Therefore, this molecule is a chiral molecule. The other one, my 2-propanol, you have 2 methyls. They are identical. As long as you have identical substituents, this molecule is considered a chiral molecule. There's a naturally occurring product. They can be also chiral molecules as well. If you have a molecule such as methane, you have 2 hydrogens can be replaced by the 2 isotopes of your hydrogen, such as one hydrogen replaced by your deuterium D, another hydrogen replaced by your tritium T. Therefore, this molecule is also considered a chiral molecule. This molecule, you consider it as a chirality with isotopes. Again, your achiral alkane can be transformed into chiral molecules by replacing your hydrogen with its isotopes, such as isotope deuterium and or isotope tritium. This kind of isotopic isomers are useful, particularly useful in the isotopic labeling, which can help you to understand the information about the mechanism of your different reactions. In your achiral molecule, in the non-chiral compounds, usually you can find 2 important symmetries. One is called the plane of symmetry, another one called the center of symmetry. So if you have your molecule, this molecule has either a plane of symmetry or this molecule has a center of symmetry, meaning the molecule will be superimposable on its mirror image. Therefore, the molecules with either plane of symmetry or center of symmetry will be considered a chiral molecule. The plane of symmetry means if you place a plane, this plane bisects a molecule so that half of the molecule is the mirror image of another half. For example, this molecule, the top half is the mirror image of the second half. Therefore, this molecule is not a chiral molecule, such as in your dichlorofluoromethane. This dichlorofluoromethane has a plane of symmetry as shown in this image. So the second one is called center of symmetry. Center of symmetry is a point. This point is the center, and if you draw the lines from this center in your molecule to the different atoms or elements, so you are going to extend the distance. For example, I have this center. I'm going to draw a line from this center towards my right to this carbon, and also draw from the center to the opposite carbon. So what you are going to find, so the distance will be equal. So therefore, you are going to have a center of symmetry. So the center of symmetry tells you there is a point which serves as your center. If any line drawn from this center to some element of the structure, what you are going to see when you extend the equal distance in the opposite direction. So this structure will encounter an identical element. For example, this center, I draw a line towards this, you encountered a carbon, and then you draw another line, you encountered another carbon. These two carbon encountered identical element carbon. The distance between that center to the carbon, they are also equal. Therefore, under both circumstances, plane of symmetry, center of symmetry, if the molecules have this, either of them, that molecule is therefore an achiral molecule. In terms of the structures, if you have the chiral molecules, you can identify the absolute position of your three-dimensional arrangement of different substituents. Therefore, you are going to obtain an absolute configuration. For example, I have my 2-butanol. So you can draw the 2-butanol in two different approaches. One, you have your hydrogen pointed away from you and your OH hydroxyl on your right-hand side. The other one is on your opposite side, on the left-hand side. These two molecules, they are mirror images. They are representing the exact three-dimensional spatial arrangement. So therefore, both molecules are called absolute configuration. So you also have some molecules, such as if I have my 2-butanol written down as what I showed. This molecule, this structure, essentially you call them relative configuration. Your compounds, particularly with the different absolute configuration, have the same relative configuration if those configurations in your chiral center is the same. The configuration of the chiral center, they are the same. So in these reactions, the reactant and the product have the relative configuration because the reaction do not affect on the chiral center. So for example, I have my 3-butane-2-ols. I have my enols. It's going to subject to the hydrogenation reaction under platinum catalyst. You are going to produce an 2-butanol. These two molecules, reactant and the product, the chiral center has not been affected by this reaction. So this both of these formulas, they are the relative configuration. So some of the configuration, you are going to identify the exact three-dimensional arrangement of all 4 different substituents. You consider them absolute configuration. The ones you didn't identify the absolute position, so you did not give the exact three-dimensional arrangement of your 4 different substituents, this related structure you call relative configuration. So also I showed you another replacement reaction. So maybe SN2 replacement reaction, nucleophilic substitution. So this one also didn't show you the configuration affected by the chemical reactions. And related to your absolute configuration, so there's some histories. In 1951, so the tartaric acid has been identified. The structure, absolute structure, was identified by using X-ray crystallography. At that time, people using positive, negative to represent it. If you have your group, the group with a higher priority, you rank it in the decreasing order. So from OH to CH2, CH3, so you are going to count it in a counterclockwise. So you are going to have the positive structure, otherwise you have negative structure. Therefore, we are going to use another special nomenclature called RS notational system. The RS notational system is based on the Kahn-Ingold prelog rules. In this configuration determination, we are going to go through 3 major steps in order to determine RS configuration. First of all, you are going to rank the substituents at your chiral center. First of all, you must have a chiral center, and then you are going to rank the substituents based on the Kahn, Ingold, and Prelog rule. So you rank the substituents, and then you are going to rearrange your molecules so that the lowest ranked substituents pointed away from you, such as if you have your hydrogen in your molecules, you place the hydrogen in the position away from you, and then you ignore this hydrogen. You are going to rewrite it into a 2D dimension structure. You ignore hydrogen, and then you are going to count the substituents, highest priority, second highest, third. So you are going to rotate it. If you figure out that this is a clockwise, if it's a clockwise, you call it R configuration. If you have a counterclockwise, you are going to have S configuration. That's 3 steps. So regarding rank the substituents at the chiral center, we are going to apply Kahn, Ingold, Prelog's rule. Normally, if you have your OH group, oxygen connected to your chiral carbon, this group will have highest priority. Your alkyl groups and your halide groups, they are essentially identical to each other, but you are going to use the different atomic number or different size to determine the configurations. If your chiral carbon connected to the other carbon and then connected to more carbons, you are going to figure out the first point of difference, and then you rank the priorities. Second step, again, you are going to rearrange your molecule by orienting the molecule, therefore the lowest ranked substituents pointing away from you, and then you ignore the lowest ranked substituents. Again, for this hydrogen, you ignore it. You put this hydrogen in the back of you, away from you, and then you are going to start the third step. The third step, you are going to alter it. You're going to alter these three other substituents in the decreasing precedence traces. If these traces from high to low, if these traces, this decreasing precedence order traces a clockwise path, you consider this configuration R. If this decreasing precedence traces a counterclockwise path, this configuration will be your S. For example, again, we use this to butanol. First of all, you are going to figure out this is my carbon, which is chiral, and then connected to 4 different groups, and then your hydrogen pointed away from you, and then you rank your 3 different substituents. My OH highest, my ethyl second, my methyl third, and therefore you are going to trace it from OH to ethyl to methyl, and then you figure out this is clockwise. You figure out this is counterclockwise. Therefore, you call it S to butanol. So normally you put your R or S configuration in parentheses, and you italic it. Use a capital letter to represent it. So this is about your nomenclature or determination of your RS configurations. So I'm going to stop at this point, and I will continue after 10 minutes break. You have a nice day. Followed by, we are going to complete your chapter 7, chiral molecules. Stay safe and stay healthy. Thank you.